Okay, we're going to take a look at a integral problem involving a variable exponent. So it says figure 6-2k shows the graph of the following function f. And then it gives me some more information. I'm going to flip pages for a minute just so I can come back and forth and not fill up the page with too much stuff. It says let g of x equal the integral from 2 to x of f of x. Oop, not f of x. Who said f of x? F of t dt. And what it says to do is, on a copy of the figure, sketch a graph of the function of g. So if I go back to my figure, I will see that I'm looking for values between, it's a lot of values, right? Between 0 and 10. So I've got to search those values out. What I'm going to do is I'm going to make myself a table of values here. I'll start with G0, G1, G2, G3, G4, G5, G6, G7, G8, G9, and G10. So I've got to find those values. And what I'll do is I'll work out the first two the long way, and we'll solve the rest from there. I'm going to start at 2 just because I have my integral sign right there with the lower, a lower bound of 2. So I know that g of x is equal to the integral from 2 to 2, because x is equal to 2, of f of t dt. Oop, I wrote dx again. That would be a Kramer. So I'm starting at 2 and ending at 2. Therefore, there's no area collected. So g of 2 is going to be 0. That's going to be my starting point. I can always anchor my starting point. I can plot everything at the end, but I know g of 2 is 0, so I'm going to put a dot there to begin with. Oop, that wasn't very good. Done. Dot. Hey, why do you keep grabbing that? That's okay. Send to back. Done. Okay, so now I have to find all the other values. And because our function is based on the integral, it's basically going to be adding up the area under the curve. So what's going to happen is between 2, I'm just going to make a line around race, between 2, 3, and 4, the new graph is going to increase because I'm adding area. Between 4 and 7 is going to decrease because I'm subtracting area. Between 7 and 10 is going to increase again because I am adding area. It's all about the area under the curve. So let's, I can just, a number of possible ways. Let's do the second part next, which says G3 is going to be the integral from 2 to 3 of f of t dt, which means I have to find the area under the graph between 2 and 3. So it's this area right here. So it looks to me like it's exactly 1 1/2 or 1.5 right up top here. Oh, that's a bad arrow. That region looks like 1.5 is the area in that region. So I'm going to come back to my graph here, and I'll find that this region is between is equal to 1.5. So for G4, I'm going between 2 and 4 of f of t dt. So I'm finding the area that's trapped between the value 2 and the value 4. And what's nice is I already know the area that's trapped between 2 and 3. I found that before. So I can just find the area between 3 and 4, and that looks like 0.5. So I'm going to add those two together. Come back to my problem here. I'm going to add the 1.5 I already have, and then add the 0.5 I just found that's between 3 and 4, and I'm going to end up with 2. Now, I can keep going this out the long way, but the nice part about this is the area of succeeding intervals is just the area of the interval before it, plus or minus the new area you're getting. So I'm going to stay off this page for a minute. I'm going to come back to my graph. I'm going to find the area of all the different regions. This area is 0.5, but is it 0.5? It's not. Why not? That's right, Quinn, because it's under the curve, so it's negative 0.5. The next one also looks like a little more than negative 0.5. I'm going to say negative 0.75. And the next, I'm just estimating, but it's a decent estimate. I think the next one's about negative 0.25. The next one also looks like 0.25. I could be off, but it's fine. The next one looks like 3/4 about, 0.75. And the region after that looks like it's about 0.25. So all I'm going to do on my chart is I'm going to add the next region on in there. So far I've done up to G of 4. So G of 5 is going to be whatever I have to that point, plus, minus this region right here. So I'm going to go back. It's going to be 2 minus 0.5, so it's equal to 1.5. So I know my next region, G of 6, is going to be the 1.5, and then whatever goes between, sorry, wrong way, between 5 and 6, I found that to be negative 0.75. And that's equal to, I got $1.50, I lose 75 cents, I got 75 cents left. I'll just carry that number on down. I can keep carrying it down and then combining on what I find in the next region. It looks like negative 0.25. 75 cents, I lose a quarter, I'm down to 50 cents. Now I'm going between 7 and 8. Looks like I'm adding a quarter on, so it's going to be 0.50 plus 0.25 equals 0.75. I'll circle all these when I'm done. G of 9 looks like about 0.75, so I'm at 0.75 plus 0.75. 275 cents is 1.5. And my last one is going to be 1.5. Oh, wrong way, boss. Sorry. Plus another, ooh, I almost messed that up. Plus another 1.25. So when I did this before, I forgot to count that 1 on there. I should be a little more careful of that. So it's 1.25. So we're going to add 1.25. That's equal to 2.75. So I'm going to circle all those really quick. The final answer so I don't confuse what's on my page. 5.75. Hey, Mr. Brigham. What is it, Matt? You notice you did not find G of 1 and G of 0 yet. I know that, and I did that for a reason. I started here because that was what my lower bound was, because I knew I was adding, as I went up, I was adding information to it. For G1 and G0, I'm going to be actually subtracting off positive values. As a matter of fact, I'll look at those now. This area looks like 0.25, oh, sorry, erase, back. Looks like it's about 1, 2.5, so we'll call this 2.5. And this region here looks like 1, 2, 3.5. So as I work backwards now, instead of, because I'm working backwards, I'm going in a negative direction with a positive area, I'm subtracting from what I had to begin with. So between 2 and 1, this is the integral from 2 to 1 of f of t. That's going to be equal to negative 0.25. Oh, I did it again, didn't I? Negative 2.5, because that's how big that was there. And then to get the next one as well, I'm going to take that off and this off. So I'm going to take off another 3.5. Negative 2.5 minus 3.5 equals negative 6. So now that I have some values, I can start plotting them. I'll plot 0, negative 6 first. I'm going to erase this here. Can't necessarily erase. I'll have to do this in blue. So at 0, it's at negative 6. Oh, it does it all the time. Hold on, I'm done. When we're at 1, we're at negative, what were we at? Negative 2.5. I know I'm flipping back and forth. Negative 2.5. At 2, we know we're at 0. So let me get the next one. It's 1.5, 2, and then 1.5. It's at 1.5, 2, and then 1.5. Now over here, 3/4, half, 3/4. 3/4, half, 3/4. And then 1.5, 1.5 and 2.75. 1.5, 2.75, and then I can connect those dots. And because these are lines, I'm going to make them straight. Terrible connect the dots. I think you get the idea, though. Now, does this blue graph make sense with the area of the graph that's here? Well, starting at 2 is when we started going forward, and we were adding area here. So the graph went up to this point right here. And then we started subtracting area, so the graph went down. And at this point right here, we started adding area again, so the graph then started back going up. And everything was contingent on this starting point right here. Right here. Then when we're going backwards, we're adding negative area, so the graph went down. So this picture matches kind of what's going on there. Remember, g of x is this is the integral of f of t. So it makes sense that the slope here is 0, and those are turning points. So now let's look at the second part of the problem. The second part of the problem says let h of x equal the integral from 2 to 2x of f of t dt. It says find h prime of 4. Well, that's not a problem. We know how to find the derivative of an integral with a variable in the exponent. H prime of x is going to be equal to, I'm going to drop this 2x right in and multiply it by its derivative. It's going to be equal to f of 2x times the derivative of the inside, which is 2. And they want me to find h prime of 4. That's why you find the function first. It's going to be f of 2 times 4 is 8 times 2. Notice this 2 is on the outside of the parentheses. It's the derivative of that function. So I go back to my graph to find f of 8. Let's see if I can find f of 8. F of 8 is the original graph. F of 8 is 0.5. It's right here. 0.5. And had I known going to the original graph, well, it told me to go to f. So I wrote f right there. H prime of 4 equals 0.5 times 2, which equals 1. So h prime of 4 equals 1. And just to kick back on a problem I looked at yesterday, they can ask me for h primes. They can also ask me for h of something. They can say find h of 2. It just means that x is equal to 2. So that's equal to the integral from 2 to 2 times x. 2 times 2 is 4 of f of t dt. And that just means I have to find the area under the curve between 2 and 4. So I'll go back to the graph. And this is different when they ask you for h, they're asking you for the area. I know I'm making dots there, sorry. So between 2 and 4, I've got this little triangle right here. And that triangle is 1/2 the base, which is 2, times the height, which is 2, 1/2 of 4. So the area is going to be 2. So the integral of this function here is going to be equal to 2. This problem is very different from this problem. In this case, they're asking about the derivative, so you drop that function in, and you use the derivative of the function to solve it that way. If they ask me about the original function, they're just asking me to find the new constraints. That 4 came from the fact that the top of the integral was 2x, and 2 times 2 equals 4. We'll watch this video at the beginning of class, and if you need any help, we'll go over some more problems.